14.4 is about integrated rate laws. Integrated rate laws are all about time. There are different integrated rate laws for first, second, or zero order reaction. You're going to have to do a little bit of memorization here to know which rate law goes with which order of reaction. There's lots of information here, but we are just going to focus on a few things. For a first order reaction, the integrated rate law looks like this. The natural log of the concentration of A is equal to negative K times T plus natural log of concentration of A times 0. Notice that this is a y equals mx plus b format, where y is equal to your natural log of the concentration of A, m is equal to negative K, x is equal to T, and your y-intercept is natural log of concentration of A times 0. So, guys, for a first-order reaction, according to this equation, if you graphed y versus x, a natural log of A versus time, you're going to get a straight line, this is a straight line equation, with the slope being equal to negative K. That is the major thing to know here. So if you see a graph that looks something like this, with your natural log of A versus T giving you a straight line, you know first off that it's a first order reaction. You know also that if you calculated the slope, it would be equal to negative K. And so you could take your negative slope and find K. The other thing that you guys need to make sure that you know is how to find the half-life of all of these orders of reaction. Half-lives are the amount of time it takes for half of your substance to disappear. Now, if you look at this great big long derivation here, we're not going to go through all of this, but the most important part is this guy right here. That's the equation that you need to make sure that you know. It says that the half-life of this substance is equal to the natural log of 2 divided by K. And so you could use that to find the half-life of any first-order reaction. Now for a second-order reaction and for a zero-order reaction, we're going to do the same thing. We're going to find a linear equation and we're going to find a half-life equation. So let's take a look at our second-order reaction. For our second-order reaction, our y equals mx plus b equation looks like this one right here. So if you graph 1 over your concentration of A versus T, you're going to get a straight line, and your slope will be equal to K. For the half-life equation, the half-life is equal to 1 over K times the concentration of A at time 0. And then if we take a look at a zero-order reaction, our y equals mx plus b equation looks like this, where if we graph A versus T, we get a straight line. Our slope will be equal to negative K, and our half-life equation is this equation right here. Half-life equals concentration of A at time 0 divided by 2K. Make sure that you know for all three orders of reactions the straight line equation, what you would graph to get a straight line, what the slope would be equal to, and the half-life equation. Now if they give you a integrated rate law and there's more than one reactant present, that's when it starts to get tricky. But they're not going to give you anything super complicated. Probably what they're going to give you is they're going to give you something where you have one reactant in really low concentration and the other reactants are a lot higher in concentration. So when that happens, you can take this rate law right here and you can simplify it down. If you have really, really high concentrations of some of these and one of them is in a really low concentration, it's the low concentration substance that's going to determine the rate of the reaction. So if A is in the smallest concentration, then A is the important one in determining the rate. So our rate law could be written like this. It's a nice way to simplify these rate laws, and this is often called a pseudo rate law. In this case, it's a pseudo first order or zero order or second order rate law. and it just makes life easier to deal with. We're going to look at together in class free response question number 2005, and we'll practice doing some of these together. In 14.5, we already know that if you raise the temperature, it tends to increase the rate of the reaction. And this is based on the idea that molecules have to collide together in order to actually react. This is referred to as the collision model. Whenever the molecules collide together, they have to have enough energy to actually react with one another. And they also have to have the correct orientation. So let's take a look at what that means. If we're looking at orientation, and I try to take a molecule like NH3 ammonia and react it with something like BF3. If the BF3 reacts with the ammonia by coming into contact with it on this side, alright, comes in contact with some of the hydrogens, no reaction is going to take place. But if it comes into contact with it on the lone pair side, if it comes into contact right there at this point, then what happens is the BF3 can attach to the NH3 and we form a compound. So they have to have the correct orientation in relation to one another in order to interact. For most reactions, there's a minimum amount of energy that is required for the reaction to take place, and this is called activation energy, which is abbreviated capital E lowercase a. And if you take a look at this graph right here, this is an energy graph. It shows the energy of your reactants, it shows the energy of your products, and it shows that in order for the reactants to make the products, you have to overcome a certain amount of energy, the activation energy. So this is the minimum amount of energy that your reactants have to be able to get in order to become products. So the difference between this state and this state is our activation energy. Now, for this particular graph right here, notice that the change in energy, or change in enthalpy, between the reactants and the products is negative. So this is an exothermic reaction. If I was going to look at an endothermic reaction, it would look pretty similar to this, only the products would be higher in energy than the reactants. But it would still have a activation energy, all right, that it would need to overcome in order to actually make the products happen. There's an equation that you can use to calculate activation energy. It's called the Arrhenius equation. The Arrhenius equation has a couple of different forms, but there's two big ones that you need to be familiar with. I'd be familiar with this one right here, but the big one to know is this one right here. Now, if I remember right, both of these forms are shown in your equation sheet on the AP exam, but you need to be familiar with it. This one right here is set up in a y equals mx plus b format, where y is the natural log of k, x is 1 over temperature in Kelvin. That's going to be equal to the negative activation energy divided by R. I've seen a problem where they asked you to calculate activation energy where they had you use this equation once. More common, though, is to use the linear equation and a graph to figure out what activation energy is, or just describe how you find activation energy using that graph. So I don't know if I would memorize these equations, but definitely memorize what they're used for and what you can use to find the activation energy if you have a graph sitting in front of you.